Hello and welcome to the 8 Forms of Corrosion course. We'll be starting naturally with module 1, and on this module we're going to be discussing stress corrosion cracking. Okay, so let's just have a walk through of the outline agenda for this module. So we'll start with an overview of the most commonly found stress corrosion cracking types that we see in a refinery context. Then we'll look at some of the earliest reports of stress corrosion cracking that have been found in the wider industry and what was learned from those incidents. We'll have a brief historical overview of some of these examples. We'll look at some of the stress corrosion cracking incidents that have happened, and then some of what was learned from that and what we've used from that learning and taken forward and applied today in some of the design aspects. That leads us into the next item, some of the mitigation that we can put into place as part of the design stage. So design, construction, and then inspection and maintenance and operation. We will give some examples, we'll cover some examples of the typical systems or areas of the plant, areas of the unit where we find these mechanisms. And for each of the main mechanism types, we'll cover a scientific sort of overview, a sort of mechanistic overview of the science that plays out when these mechanisms initiate and propagate. We'll cover each one in a little bit of detail, and then we'll just summarize at the end, and we'll look back over what we've covered and what we've learned and some of the key takeaways that you can think about once we've finished this module. Okay, see you on the next slide. Okay, so in terms of the main refinery stress corrosion cracking types, starting at the top, probably the most prevalent and most commonly found stress corrosion cracking type on a refinery is that of chloride SCC. We'll cover some of the issues that have been found in the refinery regarding chloride stress corrosion cracking. It's probably important to note that this is either found on the process side of equipment, or perhaps more commonly these days it's found externally under insulation. So it's a form of CUI, but it's a cracking risk that's found under insulated stainless steel equipment operating at some temperature above 50 degrees C. We'll cover that in a little bit more detail in the following slides. Then we'll look at carbonate stress corrosion cracking, a form of alkaline stress cracking that's found in carbon steel equipment in non-post-weld heat treated weld areas. We'll then look at ammonia stress corrosion cracking, which commonly affects copper alloy materials such as brass, etc. We'll then cover amine stress corrosion cracking. Amine has been used much more widely in recent years, and it's taken over from ammonia as a form of pH control and acid dew point regulator. And with this advanced technology, it's brought its own issues with it. So we'll go into that in a little bit more detail. Then we'll cover caustic stress corrosion cracking, and we'll look at the parameters involved and the ways in which we can avoid the issues. As with all these other mechanisms, we'll look at ways in which they can be designed out. And then lastly, we'll cover polythionic stress corrosion cracking. This is probably less common, but nevertheless, it is a particular issue for certain parts of the refinery, and we'll cover that in a bit more detail, why it occurs and what we can do to avoid it. Okay. So one of the earliest reports of stress corrosion cracking, sort of in the world really, was a form of what's called alkaline stress cracking, because it occurred in an alkaline environment, we now know, but it was at the time given the name of season cracking. And it was only given this name because it appeared to happen towards the end of or shortly after the rainy season in warm, humid climates in countries around the sort of equator area. And so only because, again, it occurred at the end of the rainy season, it was christened with this name, season cracking. People were not sure why it was happening, but they knew it happened roughly then for some reason. So in its original form, it referred to a form of delayed fracture that took place for cold worked brass, and it was noted around the start of the Industrial Revolution, circa 18th century. Now, it was first detected in India, so a warm, humid climate, and it was picked up on brass cartridge shells. So these were sort of military cartridge shells, and in those days they were kept in infantry horse barns, these shells. So that's where they were stored. So you had a sort of warm, humid environment, and you had a lot of horses that were being kept and maintained in these barns. So if you think about the horses, the shells were there, the horses would urinate, and in the urine would be ammonia, and then the ammonia vapors in the humid climate were condensing on the brass shells, and lo and behold, this was one of the earliest forms of ammonia stress corrosion cracking. Now, the brass contains copper, and we now know today that copper alloys can be susceptible to ammonia stress corrosion cracking. Now, this was very alarming, as you can imagine. We don't want to be firing defective ammunition cartridges because the consequences could be severe. So this was something that we needed to understand and get to the bottom of. So this, along with some other issues in the industry, led to a lot of research being undertaken, and that research continued for many years, and we've learned a lot, and a lot of that knowledge that we have today is used and implemented within design, operation, maintenance and inspection of these components. So another example of an early report of cracking of this nature was that occurred in mild steel riveted marine boilers. It was referred to as caustic embrittlement because of the apparent nature of the cracks that formed. It looked as though the material had become brittle. A review of those cracked locations determined that caustic material was built up behind the rivet and the boiler shell. So there were small crevice areas that are formed by virtue of having this rivet tightly fitted to the outside shell of the boiler, and those crevice areas allowed the build-up of caustic material. So then you have a hot surface, you have stresses around the aperture through which your rivet is fitted. You've got internal applied stresses as well on the boiler because it's containing pressure, and then you have what's needed to drive a cracking, stress corrosion cracking process. So those local microenvironments catalyzed the cracking mechanism. Sometimes those cracks led to catastrophic failures of steam boilers, and people were killed, unfortunately, and seriously injured. So this was a cracking phenomena that the industry needed to take very seriously and try to understand. So, how significant is stress corrosion cracking? Well, over the years, there have been a number of very serious incidents, and those incidents have been attributed to stress corrosion cracking, both in the early days post the initial identification of the mechanism, and then since then in the sort of wider industry. And as I mentioned a short while ago, unfortunately, some of these incidents have led to loss of life, and it was just this concern that the industry had that led to a lot of research. And this is probably one of the most well-studied areas in materials and corrosion, this issue of stress corrosion cracking. And it's fortunately then led to a lot better understanding, and we've been able to design out a lot of the issues, which is what we've tended to see in the industry. However, serious incidents can and do still occur, and what we'll do next is we'll just watch this YouTube video which will explain an incident that happened in the United States. So as mentioned earlier, a lot of research has been undertook to try to better understand these mechanisms because of the significance of the threat that was posed to industry from these sort of unplanned, sudden, rapid, catastrophic type incidents that would just take place without any measurable loss of thickness, without any sort of noticeable signs of deterioration, unless it was specifically identified and looked for and monitored on a regular basis with effective inspection techniques that would pick it up. So, as I said, a lot of research has been undertook, and for that reason, although major incidents have took place, these mechanisms behind them are much better understood than they were before, and the instances have dropped off quite considerably, which is good. This understanding has then been incorporated within the design of equipment and piping, the operation, the maintenance, the inspection plans that are employed, the repair procedures that are conducted. And I've got a few examples here to run through. So NACE, you may have heard of them, the National Association of Corrosion Engineers. They have several recommended practices, RPs, and a lot of all of the stress corrosion cracking mechanisms are incorporated within good practice, recommended practice guides that NACE issue. There are also company standards. So the major oil refining companies have their own company standards within which they will specify post-weld heat treatment requirements, considerations for items entering this service, caustic service, amine service. So there'll be company standards as well, which will document the requirements to avoid these sorts of mechanisms. Then there's also local standards. So there may be a number of different operating refineries inside the same group, and local standards can be developed that take into account any local specific issues that have been experienced. So a site may want to go a little bit above and beyond what the company standards have said because they've experienced a particular issue. That's fine. That's what local standards are there to do typically. Then there are piping fabrication standards, erection, installation, coating and insulation standards. Now, with regards some of the cracking mechanisms which we'll cover, some of these are external environmental stress corrosion cracking, such as chloride. So chloride stress corrosion cracking from an external environment under insulation is quite a big issue. So this is where the coating and insulation standards and cladding become very important. We'll cover some of that as well in a bit of detail when we go through this. Then there's including these mechanisms appropriately within your risk-based inspection program. That helps then to focus on identifying the appropriate techniques which are most likely to identify them, the locations that you want to target, within your inspection scope or your written scheme. And then what's very important to remember is that these standards and procedures and processes have been developed for real world problems, and that's why it's really important that we strictly adhere to them. They're not just developed because people thought that was a good idea. They've been developed because they're absolutely necessary, they're mandatory, and they should be treated with respect, and the standards upheld at all times. Okay. Another example, again, of chloride stress corrosion cracking, but this time it's process side related. So this, although it looks more like an alley brass or copper material, this is actually a stainless steel tube, 316 austenitic stainless steel. And this has suffered from external chloride stress corrosion cracking. Below you should be able to see here, this is a micrograph showing a close-up. This is the grain structure here, this austenitic grain structure, and you can see these cracks that are forming. Now, they're transgranular in nature. That's what you typically see as opposed to intergranular. You do get intergranular stress corrosion cracking, but that's normally when a material has been sensitized, and we can come on to that a little bit more when we get into the mechanism specifics. Okay, so how was this caused? What could we do to prevent it? Well, it was a cooling water exchanger. It was a cooler. It resulted in the exchanger having the tubes replaced, and we upgraded the material to prevent recurrence. So the issue was that it was getting hotter than anticipated, and there'd been a step change in the chloride content of the cooling water system because of a change of supply at the source. So that, in combination with the hotter operation, meant that we were sort of moving into the parameters within which chloride cracking became an issue, where it hadn't done previously. And in this example, when you've got a cooling water system, you can't easily control or change the cooling water content without significant investment. So putting filters in and all the rest of it. So the most cost-effective means of mitigation in this example was to upgrade the metallurgy of the tubes to a more chloride stress corrosion cracking resistant material. So there are super duplexes that can work. It just depends on the chloride content and the temperature, as well as nickel alloys and things like that, which will help mitigate this. This is another example, again, from industry. This is amine stress corrosion cracking. Now, if you have a look at that photograph, you should be able to see where the cracking has occurred. Apart from the nozzle, you should see that it's actually occurring. It's occurred here along the toe of the weld. Okay, so it's occurred along the toe where there is ample inherent stresses, close to yield in some cases, where the material is put under a great deal of internal strain and stress because of the welding operation as it tries to contract once it cools. This is a carbon steel nozzle in a carbon steel column, and this is an amine service. So typically these days we would post-weld heat treat, so we'd stress relieve carbon steel that was in amine service, but this column had been in service for 20-30 years, and therefore wasn't really a major issue at the time, this cracking phenomena, and therefore it wasn't something that was incorporated within the design. So it wasn't post-weld heat treated. So we had this issue, and then we had to to work out an engineering solution to try to resolve the problems with advanced welding techniques using nickel-based weld consumables to help eliminate the cracking problem. Okay. So we just saw on the previous slide that this active to passive or passive to active transition is where we see this, where we see stress corrosion cracking happening for active path dissolution. So again, there's another diagram showing the active corrosion shown by E1, which is where we're increasing the potential and the log of the corrosion current is increasing steeply as we climb up to that very top. And then we see a sudden drop as the material passivates and the corrosion current is essentially stops or is retarded and becomes very low. That's when the material has become passive, okay, as we move from E2 to E3 as shown on the diagram. Again, it's this sort of E2 to E3, almost sort of top end of E1, where this transition period occurs, and this is where we get this cracking phenomena. And what's happening is that, as we described earlier when we looked at this process in a little bit more detail, the crack tip remains active. What's happening at the crack tip is the material is yielding, and that's exposing fresh, unprotected, and when I say unprotected, I mean unpassivated material, and that forms the pathway for the corrosion to continue. Meanwhile, at that active to passive transition sort of region, we have the crack walls that remain passive. That's due to the electrochemical potential that the material has adopted. So again, we've got this cathodic surface area, which includes the crack walls and the surrounding base material, and then we've got a very concentrated tip of anodic corrosion current, which is corroding the tip only, which is helping to drive the crack and propagate the crack along that sort of corrosion line, if you like.